Radical expression is another name for square root. That's all that is. Sounds fancy. The square root. When you get into Algebra 2, you'll do radical expressions that are bigger roots, like cubed roots and fourth roots and fifth roots and things like that. So radical expression is just a general term for that. It's kind of like, shoes is a general term that encompasses sandals and sneakers and boots and all that. It's shoes, things go on your feet. Radicals are just roots of some sort. We're dealing with Algebra 1, square roots. But Algebra 2, you get bigger roots out of that. So radical expression just means a root symbol, and we're dealing with square roots, and we'll have a number in here that's inside of that. So what we're going to do is take that square root and we're going to simplify it. We're not going to type it into a calculator and get the decimal for it. We're going to simplify the square root so that we get an exact solution. Now, sometimes it's super easy, like the square root of 25. That should be common math knowledge for you guys at this point in your life. What is the square root of 25? Why? Because 5 times 5 is 25. That it takes 2 5s to make a 25. You multiply. That's the reason. Here's the kind of the precursor to what we're going to do with numbers that are not nice and square roots. I remember doing factor trees when you were in elementary school. That's the easiest way to simplify a square root. There are other ways, but I think this is the easiest way because this is the same way you're going to do cubed roots and fourth roots and things in Algebra 2. Okay, so if you learn this method making factor trees, and that's something you've done before, and it's not hard to do, then you make a factor tree for 25, it's 5 and 5. There's a pair of 5s. So that pair of 5s is what makes the square root of 25 5. You're looking for pairs, sets of 2, because it's a square root. When you do cube roots later on in Algebra 2, you'll look for sets of 3. Fourth roots, you'll look for sets of 4. And it keeps going. The bigger the root, the more need to be in a set. Okay, so square roots, we're looking for sets of 2 to get there. Okay, when we get a number that's not a nice square root like 12, small number, but it doesn't have a nice square root. If it were 16, hey, the answer's 4. But it's 12. What we need to do is make the factor tree for 12. So give me 2 numbers that multiply to be 12. 3 and 4 is a good one. 6 and 2 would also work. It doesn't matter which pair you pick, as long as they multiply to be 12. If we do 4 and 3, that works wonderfully. 6 and 2 would also work. Okay? We'll do it with 6 and 2 in just a second. I'm going to do it 4 and 3 first. Okay? Now, is 4 prime? What's it mean to be prime? Nothing else can go into it besides itself and 1. 4, 2 goes into it, right? So we break down the 4 because it's not prime as 2 times 2, right? 3, it's prime. Nothing else goes into it. So we know 3 doesn't break down any further. Now we look for pairs because everything at the end of the branches on the factor tree is a prime number. That's how you know you're done with the factor tree, right? Remember that? Okay, so there's a pair of 2s right there. It doesn't matter that they're on the same kind of trunk of the tree. They don't have to be. There just has to be a pair. There's a pair of 2s. What that does is it puts a 2 on the outside of the radical, and then the 3 that doesn't have a buddy stays in. If you got a pair of them, one of the representative for that pair can go outside. If you don't have a pair, they're a partner to pair with, you have to stay in. Okay? So as we're making our factor trees, we got to make sure the ends of our branches are prime numbers. If they're prime numbers, you're done. And then you look for pairs. Okay? So let's look at a number that's slightly bigger than 12, but a similar kind of way of doing the square root there. Let's look at the number. Well, we're going to do square root of 12 with 6 and 2. Let's do that first. If we did 6 and 2 to start off with instead of 4 and 3, which one of those is prime? 2. So that means I need to break the 6 down. What does 6 break down as? 3 times 2. It's multiplying, not adding. So be careful. That's the most common mistake when we're doing factor trees, is instead of, when you do your branches, you, instead of multiplying, you accidentally add. So 3 times 2 is 6. Now, same idea. Once you get the branches to primes, you look for pairs. There's a pair of 2s. They just don't happen to be on the same trunk, but that's okay. There's still a pair of 2s. So the square root of 12 is still 2 square root of 3. It's the same answer as that one, even though we started with a different multiplication at the beginning. The idea is get to the primes. Let's look at 18. For example, C. What 2 numbers could we use to multiply to be 18?
9 and 2.
9 and 2 is a good option. What would be another option?
3 and 6.
3 and 6. Either of those work. If I do 9 and 2, will either of those break down further? 9 is 3 times 3. Okay. Now, 3's prime, 3's prime, 2's prime. I'm done with my factor tree. Look for pairs. There's a pair of 3's right there. What goes on the outside of the square root? 3. What's on the inside? A 2 that doesn't have a partner. So the factor tree part, that's something you did in elementary school. Probably haven't done that in a few years. Maybe. I don't know if you did it in junior high or not. But you've done those before. That's something we've taught you over the years to do. And it makes simplifying square roots super easy. Let's do a bigger number. Let's do 36. Does anybody know the square root of 36? 6. We happen to know that. It's got a good that. But what if I forgot that? And the instructions said simplify, and I got in this mode, and I've been doing a bunch of them, and my brain just didn't recognize, hey, 36 is the square root of that 6. What if I did it this way, and I didn't do 6 times 6? I did, what else multiplies to be 36 besides 9 times 4? What if I did it that way, and I just didn't remember that the square root of 36 is 6? Well, we know 9 breaks down in 3 and 3, and 4 breaks down into 2 and 2. There's a pair of 3's and a pair of 2's. So 3 times 2 is 6. That same square root that we memorized years ago. So the process is there. It's not so much memorizing things like we memorized our multiplication facts. At some point in life, we've memorized our some of these square roots over the years. Maybe some of us memorize more than others, but that's okay. It doesn't matter. The factor tree works no matter what. Okay, let's look at another one. Maybe a larger number. The square root of 108. Okay. So, what do we know about the number 108? It's what? It's big. Okay. Not real big. If I gave you $108 to live on for a month, would you do it?
No.
Probably not. So it's not big enough for that. It's even. That's a good thing to recognize. So if it's even, what do we know goes into it? 2 goes into it. 4 also goes into this one. But 2, because it's even, the rule for being even is that it's divisible by 2. So even if I don't know anything else about the number, if I know it ends in a number that's even, then the problem is divisible by 2. So I'm going to divide that by 2. 54. And now I got a smaller number to work with. What do I know about 54?
It goes into 6 times.
What goes into it 6 times? 9 does. We know something about 54, a little bit more than we knew about 108. 9 times 6. Well, are those prime? No, they'll break down further. So let's break them down further. 9 becomes 3 and 3. 6 becomes 3 and 2. All right? Now, this 2's prime, this 3's prime, this 3's prime, that 3's prime, that 2's prime. I'm done with my factor tree. Everything's a prime number at the end. So the only places I'm looking for pairs are at the ends of the branches, right? So we're looking for pairs of 3's and pairs of 2's because that's the only numbers that are there. So I've got a pair of 3's right there. And then this 2 and that 2 join together to make a pair of 2's. So on the outside of the square root, we've got 3 times 2. which will be 6. What's left on the inside? Why a 3? Okay. Yeah, there's one that doesn't have a partner right there. He's hiding in the middle there, but it's right there. That guy right there goes back on the inside because he didn't have a partner to go outside with. Okay, 3 times 2. Tyler's already told us that was 6, and we got 6 square root of 3. That's it. We've simplified the square root of 108 to be 6 square root of 3. 6 radical 3. You may hear me say both of those things as I go here. Okay. Let's try another one. Let's go to what I think is a pretty interesting number, 48, because it's real close to a square, right? If it's 49, we'd get 7 and we'd be done. But it's 48, and there's a lot of things that go into 48. What do we know about 48? It's even. So how many times does 2 go into it? 24 times. And there's nothing wrong with using a calculator to do that division. 48 divided by 2 is 24. But what do we know about 24? It's also even. So 2 goes into it. How many times? 12. What do we know about 12? 6 goes into it 2 times, right? And what do we know about 6? 2 goes into it 3 times, right? So just by dividing by 2 a bunch of times, we broke that down with the factor tree. Okay? So then, once we get all of the factor tree done, everything's prime at the end, we start looking for pairs because we're doing square roots, pairs. All right, so I got a pair of 2's right there. I got a pair of 2's right there. So that's going to be what on the outside? 2 times 2 is 4. And what's on the inside? This 3 that doesn't have a partner. The 4 times the square root of 3 is what's left. 4 radical 3, or 4 square root of 3 is what we're getting there. Okay. Anybody can type a square root of 48 into your calculator and get a decimal for that. But at some point, you've got to stop writing the decimal numbers, right? So you've got to round at some point. What we're finding are the exact solutions that are not rounded at all. And when you go into quadratics and you got an equation that deals with, you don't need a rounded value to get the y value that goes with it. You need the exact value. And when you start dealing with triangles in geometry next year, you need the exact value so that you don't mess up the angle measurement because you deal with triangles here. And if you round it, it can mess up the angle measurement. And the angles and the sides all relate in triangles. We'll learn that in geometry. So that's why we're doing this. It's got a lot to do with future things you're going to do. So let's take a number like 132. Something we maybe know something about, maybe we don't. What multiplies to be 132? Huh? It's even. Is there something bigger that we could divide by, though, besides 2? Because we did 2 on the last one. I'm just trying to stretch you a little bit, make you do something different. 4 goes into it. 8 would go into this one as well. 11 and 12. That's the one I was fishing for because that's a common multiplication table that you should know. You should know your multiplication tables up through 12s. So 11 times 12 is 132. And that's going to make our factor tree go a little faster than if we had used 2 or used 4 or used 8 because they're bigger numbers. So we got 12 and 11. What do we know about 11? It's prime, so we don't have to do anything else to the 11. And 12 we know quite a bit about. 4 and 3 or 6 and 2, whichever way you want to do that. And 2 and 2. So here we have a pair of 2's. So what's going on the outside? What's on the inside? 3 and the 11. Both of those. And we're going to multiply them back together on the inside. So that's going to be 2 square root of 33. Anytime there's more than one thing that comes out, you multiply them together on the outside. Anytime there's more than one thing still inside, you multiply them back together. Everything that you're doing in factoring or simplifying square roots is all dealing with multiplication. So wherever in doubt, multiply things, okay, when you're dealing with simplifying square roots. It's all multiplication that you're doing. Let's take the number 216. That's a good number. It maybe you know something about. I don't know if you. It's even. That's true. So we can take that route because I think it's a big number. So we can get it down half of what its normal size. That would be easier to deal with. Oh, what's 108? We've dealt with 108 before, right? And let's think about a different way to break down 108 instead of using the 2 that we used before. What? Say it again. 12 and 9. Perfect. Good job. 9 times 12 or 12 and 9, no matter where you put those. 9 we know about. 12 we really know about. And then start picking pairs. Pair of 3s, pair of 2s. Hey, this 2 and this 3 don't have a buddy. So we got 3 times 2 on the outside and 3 times 2 on the inside. 6, square root of 6. Good job. Not too bad. The key is getting your factor tree built right. Don't make the mistake of doing addition instead of multiplication. Everything you're dealing with here is multiplication. That's the operation of the day, is multiplying. Everything you deal with is built from multiplying. Okay, let's take a slightly bigger number that has some interesting things happening to it. If you simplify it in a square root, like 256. 256, fairly important number when you think about computers and electronics and things. Yeah. It's even. True. How many times 2 go in 256? 1, 2, 1 left, 128. All right, so that got it half as big. So maybe we can work with 128. Okay, 2 goes into that, so we get 128 a little smaller. 64. Now, what do we know about 64? It's 8 times 8. We know that. It's even. We could do 2 times 32 if we wanted to, and then go from there. But 8 times 8 might speed us up a little bit. 8 is 4 and 2, and 4 is 2 and 2, and the same thing over here. 2 and 4, 2 and 2. All right. Now what do we do? Line the groups. Pairs of 2s. Okay, so I've got down here at the bottom of the way I wrote my tree, I've got 3 pairs of 2s there, and then there's a pair up there, right? The 8s don't count because they're not what? Prime. Remember, you can only look at prime numbers when you're counting up your stuff. Okay, don't forget that. I'm glad that came up because you've got to make sure you're only looking at the primes. The 8, the 64, the 128, they're not part of the game anymore. Just like 256 is not part of the game anymore. We're only looking at the prime numbers. So we've got 1, 2, 3, 4 pairs of 2s. So that's 2 times 2 times 2 times 2. And anything left on the inside? 4 is not a prime. It's not part of the game anymore. 8's not a prime. It's not part of the game anymore. 64 is not a prime. It's not part of the game anymore. 128 is not a prime. Not part of the game anymore. So is there anything that doesn't have a buddy that's prime? No. So there isn't anything left on the inside. 2 times 2 times 2 times 2. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. 2 to the 4th power is what 256 is. Why is that important when it comes to electronics and computers and stuff? Anybody know? Anybody interested in that kind of stuff? It's pretty cool. Electronics, anything electronic, deals with ones and zeros. 1 is on, 0 is off. That's only 2 possibilities, right? So when you start talking about binary code is what that's called. Ones and zeros. It's a series of ones and zeros. 256 gigabytes. You wonder why? Hey, the biggest phone you can buy is like 256 gigabytes. Maybe bigger now. I don't know. But recently, iPhones, that was the biggest you could buy. Was 256. But it's because the ones and zeros, only the 2 possibilities on and off. When you start adding up all that storage, it's still electronic information. It's ones and zeros. It's only 2 possibilities. So when you start building more of them, it's still going to be a power of 2. And that's what 256 is. 64 gigs, that's common. 8 gigs, that's the lower end of the, when you talk about Apple products, and I know a lot about those, so that's what I think about, 8 gigs. I remember, I think my wife bought me my first iPod years ago. It was like, I think it was a 4 gig iPod was what I had. Now, 4 gigs wouldn't even get close to holding it. It held more than all of my music at the time. Wouldn't even get close now. But, it's just, that stuff intrigues me. I think it's fun to think about how these numbers that we deal with, how they relate to things that we're doing. So let's look at one that's a little smaller number, but a neat one to deal with is the square root of 27.
3 and 9.
3 and 9, that's what multiplies to be 27. That's good. What else? 9 is 3 and 3. Pair of 3s. So what's the final answer there? Say it again, Caitlin. Square root of 3 parts, right. A representative from that pair is all that goes out there. So it's 3 square root of 3. One representative from that pair is what goes out there. Okay. Let's do 54. That's a good number that has some interesting things happening with it. 54. If it was 64, the answer is 8 and we're done. But it's 54. We got to know something about 54. 6 times 9. We know 6 is 3 and 2. That's right. 9 is 3 and 3. We just did that. So pairs, I got a pair of 3s. But these 2 are left over. Square root of. Yeah, you're going to multiply that 3 and 2 back together and get that 6 back inside of there. 3 square root of 6. All right. Okay, with numbers, factor trees. That's the game. It's factor trees. Let's start doing letters. It's algebra. Okay, so let's do some letters inside of square roots. Let's do an easy one first. X to the third power. Now, since it's a variable, we can't really do a factor tree for it, right? And so what does x cubed even mean? It means x times x times x. 3 of them, right? That's what cubing something means, right? So x to the third power means x times x times x. Well, hey, is there a pair of x's there? There's one pair right there. That x can come out, and then this one doesn't have a partner, so he's got to stay in. Not too hard. Now, why does that work that way? When you're taking a square root, you're looking for sets of 2. When we're dealing with variables, they're going to write that with exponent notation, with exponents on it. If you divide 3 by 2, like old school elementary school stuff, like 3rd grade division, 2 divided into 3. How many times does 2 go into 3? 1 time, and then you say 1 times 2 is 2, and you subtract, right? And then to get a 1, and we used to do this. I remember doing that with the R and the 1. Been a long time since you did that, probably. But you've done it. Here's what that means. This one that was the quotient, that's the one x that's out here. This remainder is the one x that's on the inside. Let's look at that and how it works for maybe x to the 5th power. If I do that same math, instead of writing out 5x's and circling pairs, if I said 5 divided by 2, because I'm doing square roots, so I'm looking for sets of 2. How many times 2 go into 5? 2 goes into 5 2 times. And we're subtracting 4. There's 1 left. So there's a remainder of 1. So that would be x squared on the outside with 1x left on the inside. If we wrote that out and circled pairs, we get the same answer. X, 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 x. 1 pair, 2 pairs. That's the x squared that's on the outside. And then this one guy that doesn't have a partner still on the inside. Same deal with the division, but I think the division's quicker. And we're all about getting things done faster, right? And being able to look at something and do it instead of writing it out and having to, draw it. That's the next level we got to get to. What if they put x to the 6th and y to the 7th? They threw 2 variables in there. Go. Same rules. Just do it twice. 2 goes into 6 how many times?
3 times.
Remainder? Is there a remainder when you divide 6 by 2? No. Are there any x's left on the inside? No, because there's no remainder. So that would be x to the 3rd power on the outside. How many times does 2 go on into 7 for the y? 3 times. So that'd be y to the 3rd. And there's a remainder of 1. So how many y's are on the inside? 1. All just dividing by 2. And you guys were doing that a lot with numbers, bigger numbers, much bigger numbers. Your exponents aren't going to be that big. They're not going to throw x to the 765th power attention. They're going to give you like x to the 4th and x to the 9th and things like that. Okay. Is that the donut example? Let's take the number let's do 84, x to the 9th, y to the 8th. So they put a number and variables in there. Do we know how to do if it was just square root of 84? What do we do? Factor tree. Exactly. We do the factor tree if it was just, if I covered up this chunk and just had square root of 84, we do a factor tree. Well, just because that stuff's in there doesn't change the rules. We're still going to do a factor tree for the 84. So let's do that part first. Because I think that's harder than the variables. What multiplies to be 84? 21 and 4. That was one I did not think of. Good job. What do we know about 21 and 4? 4 is 2 and 2. 21 is 7 and 3. Okay, good job. Now, pairs. Pair of 2s. So that's going to be a 2 on the outside. And then I'm going to leave some space because I think I'm going to have some variables that are right there. And then what's left on the inside? 7 times 3 is back to being a 21. So a 21 on the inside. We're done with the 84. Done the hard part. Now, how do I do the x to the 9th? 9 divided by 2 goes 4 times. So that's x to the 4th with a remainder of 1. So there's an x on the inside. What about the y? 4 times, and is there a remainder? No. We're done. it looks like that's a lot of hard work, but it's elementary school math. All of it is. Factor trees, that's elementary school stuff. Dividing by 2 and getting a remainder, elementary school. Stuff you did years ago, but here you are as a freshman in high school and you have to do it again, but in the context of something else. Okay? Let's go to a bigger number. And we got 2 more and we're done. Okay? This is one of the 2. Oh. Let's say square root 384 x to the 4th y to the 11th. 384, biggest number we've done all day. So, but how do you eat an elephant? Anybody know? One bite at a time. Okay. Only way to do it. So what do we do with the 384?
Do the factor tree.
Do the factor tree. What would be a good way to start with 384 since we don't know much about it? 33. Okay, that'd be one way to do it. How'd you come up with that? Just guessed and tried some numbers with the calculator. That is absolutely a wonderful thing to do. That is perfectly fine. All right. What would most of us say? Kelly, that is perfectly great. I'm going to use a smaller number because what most everybody else would do. We know 384 is what kind of number? That's prime, not prime. It's even. So most of us would start with just taking it and dividing it by 2. We're going to get the same end result as Kelly's going to get when using her, 12 and 32? Is that what you said? So I'm going to use 2, and that'll go 1, 9, 2. And then 2 goes into 3 one time with the remainder of 1. 3 goes into 18 9 times, and 2 goes into 18 9 times, and 2 goes into 4 2 times. And then 192 we know is even as well, so I'm going to divide that by 2. That'd be 9 and 6. 96 is 12 and 8. 12 is 6 and 2. And that's 3 and 2. And 8 is 2 and 4. So Kelly, if you did it your way with the 32 and 12, you're gonna have the same number of circles, you're just not gonna have as many. They're gonna be kind of grouped a level, a little differently. So this is doing it with Kelly's suggestion, which is absolutely works the same way. You still have 1, 2, 3, 4, 5, 6, 7 2s. 1, 2, 3, 4, 5, 6, 7 2s, and 1 3. Same end result. The end of the tree is the same. What the branches look like are a little different, but the end result's the same. Now we start looking at pairs. Got a pair of 2s. Got a pair of 2s. Got a pair of 2s. 1, 2, 3 pairs of 2s. So that's 2 times 2 times 2. Leave myself some space for the variables. What doesn't have a buddy in my factor tree over here? 3 and 2. So that's going to be what on the inside? 6. Okay. 384 is a big number, so the factor tree is going to be long. It wasn't quite as long, maybe doing it this way as it was the way I did it, but you still end up the same end result. 3 pairs of 2s. Okay? How many times will 2 go into 4 for the x to the 4th power? 2 goes into 4 twice, so that's x squared. How many times does 2 go into 11? 2 goes into 11 how many times? 11 divided by 2 is 5 with a remainder of 1. So 2 times 2 times 2 on the outside is 8 x squared y to the 5th square root of 6y. That's the final answer of that one. So again, variables and numbers in there. The number part's still a factor tree, always. You're always going to do a factor tree for a number. The variables, you're going to divide the exponent by 2. In Algebra 2, when you get to cube roots, you're going to divide that variable by 3. 4 for fourth roots. 5. But the math's super easy. Arithmetic is that there are places to make mistakes, no doubt. But overall, it's not an incredibly hard concept. Let's get last one. And this one starts with something already on the outside, like a -3. And then it has a number like let's do 84. That one does some good stuff. They may have done 84 already. We did 384. I can't remember did 84. Okay, so now the 3's on the outside. So is it inside the square root?
No.
No. So we don't do anything with it right now. It's just hanging out, watching what's happening. Okay? Do the factor tree for the number that's on the inside of the square root. Okay, so we're doing a factor tree for 84. What do we know about 84? 12 and 7 is the common multiplication problem that got it there. I know my 7's times tables. 7 times 12 is 84. And then what do I know about 7? It is prime. 7 is prime, so I'm not going to break it down. But 12, I've done a lot today. So 2 and 6 or 4 and 3, doesn't matter which way you want to do that. I'll do 4 and 3. And then 2 and 2. Because it puts my pair of 2's right there together. That's why I usually use 4 and 3 for 12. Look for pairs. Got a pair of 2's. And I got 3 and 7 that don't have buddies. So that's going to be 21. Where is it at? Inside of the square root. That's right. Good job. Good job. Now, on the outside of the square root, there's already a -3. And then what else is coming out there? The 2. What operation is the name of the game today? Multiplication. And factor trees are built by multiplication. That's exactly what we're doing, multiplying. So anything that was already out there multiplies to anything you bring out there. So -3 is already there. I'm bringing a 2 out. I'm going to multiply those 2 together to get -6 square root of 21. That's the simplified version for that one. So anything that's already outside, multiply it times anything you bring outside. Okay? Like when you go outside, if the sun is shining and you go outside, guess what's shining on you? The sun. It's raining right now. Guess what happens if you go outside? It's going to rain on you. Okay? So that operation is going to happen on anything you bring outside. Okay?